Welcome back to our discussion. It's a continuation of mathematical induction. Hope you watched the previous video where I introduced the topic. This is Namakando Academy. Make sure to subscribe, like, share our videos. Also consider leaving a positive comment. All right, so let's get into solving questions based on what we discussed last time. So here we have a question which has three parts, as you can see on the board. Please make sure that you follow all the steps closely. I will do A. After I do A, you'll be pausing to see if you can attempt any of the remaining two questions. Okay, so we have a question which states, use mathematical induction to prove each statement for all positive integers n. So like I said, every time you are supposed to prove, and if it's mathematical induction you're supposed to use, they'll always state that you use the same mathematical induction. Okay, now here you're taught to say, we're proving these statements, and the condition we're given is that every value of n we have belongs to a set of positive integers. These positive integers are just natural numbers, which we have as 1, 2, 3, 4, until we move up to infinity. Okay, let's look at the first one. The first one is a series that we have on the left, where we have 1 plus 2 plus 3 plus. So these dots here tells us that there are numbers here, but we can't write all of them. But we need to proceed, and the last term we have in this series is n. That's the last term we have, and we've been told to say n belongs to a set of positive integers. And if you add all these terms, starting from 1 up to the last one, which is n, the result you obtain is n multiplied by n plus 1, then divided by 2. All the statements that you can see here, they are all correct, but let's prove how correct they are. And what we're using is mathematical induction. Let's start with the first one, A. Going to write it on this other part. C is 1 plus 2 plus 3 plus the last one, which is n. This is equals to n plus 1 divided by 2. Okay, so if you watched the previous video, we looked at the three cases. First one being proving for n is equals to 1. Then if that one is true, you then proceed to the second case where you assume that n is equals to k. Followed by that is the last step where you test for n is equals to k plus 1. After that you conclude. Alright, let's start with the first case, or rather the first step. Step 1, you test for n is equals to 1. So what you are supposed to do is, every time you're answering a problem under mathematical induction, you are advised to be indicating either step or case. Okay. So step 1, we're testing for n is equals to 1. This statement we have has an equal sign here, which tells us that the amount we have on the left-hand side is the same as what we have on the right-hand side. And if we are going by step 1, where we're testing for n is equals to 1, it means that upon substituting wherever there's n with a 1, both on the left and the right, the result should be the same. And if the results are the same, it means that case 1 holds. Okay, so let's look at this one. Now, since it is n we are testing for, it means that on the left-hand side of our statement, which is here, we're only going to consider the part which has n. So on the left-hand side, we're only getting a part which has n, since it's the one we're testing for. And based on the testing we're doing, we're substituting n with 1. So if we replace n with 1, we just get a 1. This is what we have on the left-hand side. Let's see if we're going to obtain the same result on the right-hand side. Right-hand side is n multiplied by n plus 1 in parentheses divided by 2. So like what we did on the left, substitute with a 1 whenever there's n. So this gives us 1. 1 plus 1 divided by 2. So 1 plus 1 simply gives us 2. So this will be 1 plus 1 is 2. So you have 1 times 2 here. over 2. So this and that cancels, you are left with 1. And now you observe that left and right are giving us the same result. So we therefore state that case 1 holds. So this is true by the first case. Let's now move on to the next case. Case 2. This one is an assumption. So we assume n is equals to k. So this only works if the first step holds. So we assume that n is equals to k, meaning that from our statement we write it the way it is, but wherever there's n, since n is the same as k, you are going to replace with a k. So this gives us 1 plus 2 plus 3 plus k is equals to, okay. So that's what you're required to do on the second case. Then you proceed to the next case, which you can also define as a step. So the last case, which is case 3, here you test for n is equals to k plus 1. Okay. So now this is where most challenges comes in, where proving is concerned. So please make sure you pay attention to what we want to discuss. In this first case, we substituted n with 1, and we discover that both sides are giving the same result, which was 1 on both left and right. Then for the second one, it's an assumption. Just wherever there's n, substitute with a k. For the third one, we're testing for n is equals to k plus 1. So this is what we're going to do. We get our statement, which is 1 plus 2 plus 3 plus until the last one, which is n. And in this case, our n is equals to k plus 1. So we're going to replace with k plus 1. This is equal to, here where there's n, we replace with k plus 1. Then this is multiplying with, here where there's n, we're replacing with k plus 1. Then not forgetting that this k plus 1 is just the substitution for n. Now not forgetting that we have another one, which we're adding, then everything divided by 2. Like what we have is, since our n is equals to k plus 1, wherever there's k plus 1, wherever there's n in our statement, you replace with k plus 1. So this is what we've done. Now from here, simplifying this a bit, we can write the left hand side the way it is. This is equal to, here we have k plus 1. So this side is k. 1 and 1 will be added together, give us 2 divided by 2. So this is what we have. Okay, now again, let's go back to the left hand side. This that we have is a series. It's a series of terms. So we have 1 as the first, second is 2, 3. So if you look at this, they have something in common, and that is a difference. So the difference between 1 and 2 is 1. The difference between 2 and 3 is 1. So I mean that for each successive term, you keep on adding a 1 if you want to know the next term. But if you want to go back to the previous term, if you want to move from 3 back to 2, we need to subtract a 1. So that's the behavior throughout this series we have on the left. The last part is k plus 1, which therefore means that the term which is just before this one is less than k plus 1 with 1. Meaning that if this is k plus 1, the term before k plus 1 will simply be obtained by simply saying k plus 1 minus 1. The same way we would find 1 if we have 2. It would just say that 2 minus 1, it will give us the first term. And if we want to move from 3 to 2, we just say 3 minus 1, and it will give us 2. Which therefore means that for us to move from k plus 1 to a term which is just before k plus 1, like what we are doing here, we are required to subtract a 1. So this will therefore mean that this one and this one will go to 0. So we are getting a k. So I mean that the term which is just before k plus 1, the next term before k plus 1 is k. Meaning that we can write this as 1 squared. This is 1 plus 2 plus 3 plus k plus the last one, which is k plus 1. This one is equals to the right hand side, like this. Hope you are following these steps closely. Now from there we proceed. Now let's observe again. So if you observe, this part we have formulated here on the left hand side from 1 up to k. We have it in the second case. It's the same left hand side we have. From 1 to k, we have it here in the second case. And the result is equals to k times k plus 1, then divided by 2. This is based on us concluding to say case 1 is true. Since case 1 was true, it means that even case 2 is correct the way it is, like this. So meaning that this part is indeed equal to this. Meaning that where we have 1 plus 2 plus 3 plus the other terms which are not indicated, then plus k. From the third case, which is this one, we can replace with that since they're just the same. So I mean that from 1 up to k, this sum here will be replaced with that. So we're going to obtain k plus 1 divided by 2. Now, not forgetting that there's a last term we have here, which is k plus 1. Now, this gives us our right hand side, which is k plus 1, k plus 2. These two are multiplying, divided by 2. Okay, so hope you're following the steps closely. From here, what we do next is we'll work with the left hand side, simplify the left hand side. Our end result should be what we have on the right hand side. And if this is not the case, it therefore means that this is not true by mathematical induction. And if we get same result on both sides, it means that the statement is true by mathematical induction, since it is mandatory that you end with concluding. So let's work with the left hand side. Left hand side is k plus 1, everything divided by 2, then plus k plus 1, like this. So this is a fraction. Adding together this, so we're going to combine them together and express them as a single fraction. How do we do that? We find common denominator. Our common denominator from basic mathematics here is a 2. Then we know the mathematics. You simply get this denominator for the first fraction, divide it into the lowest common multiple, which is 2. 2 into 2 give us 1. Then this one will multiply with the numerator. And when you multiply any value with 1, it will give you that same value. So we're going to obtain k plus 1, like this. Then we have plus 1 into 2 will give us a 2. Then 2 multiply with the numerator. This is our result. Okay, hope you are following me closely. Now from here, this is one part, but the denominator has 2 parts separated by a positive sign there. Now the thing is that if you look at these two, the first part and the second part, they both have something in common, and this is what we have in parentheses, which is k plus 1. And from algebra, we know what to do here is to simply factorize k plus 1. So k plus 1 will be factorized, and upon factorizing k plus 1, we will now write the remaining values, which is for the first part we are left with k, then add with the last part, which is a 2. Overall divided by 2, like this. Now if you observe, this part, which we've obtained on the left hand side after simplifying, is the same result we have on the right hand side. So since they are the same, it means that this statement is true by mathematical induction. So our third case holds. So since this third case holds, it means that we can now conclude. We can now write our conclusion. Our conclusion is that the statement is true by mathematical induction since left hand side of the third case is the same as right hand side. So you can do the conclusion there, you understand it, but the conclusion will be based on our findings. If left is the same as right, then it means that our statement is true by mathematical induction. Alright, so let's proceed to the next problem.